the fundamental theorem of calculus in n dimensions. Fundamental theorem of calculus. But let's view it now in a point vector situation. There's our region, and there's our normal vectors to the region, all in R1. Going to R2, we have Green's theorem. Green's theorem has two expressions, one as a divergence in R2 and the straight Green's theorem. When you generalize into R3, now it's Stokes' theorem, and now the normal has to be consistent with the orientation. Going into R3, we have the generalization of Green's theorem. All of these are subsumed by differential forms. In the differential form language, this is Stokes' theorem. The Gauss-Green theorem, or the divergence theorem, or the generalized Green theorem, all these names are used. And then Stokes' theorem. And all of these require the fundamental theorem of calculus, and as we saw with Green's theorem, it's just a fundamental theorem on the parameter domain. We won't do the proof because it's the same, just more technical. What we do need to do is explore what an orientable manifold is. We have to be able to define a consistent boundary, a consistent normal. So we'll start with the surface in 3 space. This generalizes into more dimensions, of course. This parameterization function is now called a chart. Either the function or the function with its domain is called the chart. And we have another one. Their union is called an atlas, and it covers the whole surface. Where the two charts overlap, these composition functions must be continuous. This is called the transition function. The surface is divided into 2 types of pieces, the overlap piece and the 2 pieces that are just one chart only. This kind of structure is called a manifold. A function that's continuous and its inverse is also continuous is called a homeomorphism. We want more structure, so we want to look at differentiable manifolds because we want to be able to look at point vector spaces everywhere on the surface. In that case, we want the function and its derivatives to be continuous both directions. That's diffeomorphism. Now to look at orientation. Positive axis to positive axis, that's the positive orientation, which gives you a right-hand rule normal. Same for the other chart. Positive orientation, inducing a right-hand rule normal. On the overlap, the interior pieces cancel out, because as you go one direction with G, you go the other direction with F. Those pieces go away. Now we want to be able to make sure that the normal transitions consistently from the blue to the gray. Instead of differentiable, we'll just say smooth. So this is what we'll be looking at, an orientable smooth manifold, where the smoothness is however many derivatives we need the thing to work. And so this transition function is just called a smooth function. To make the orientation preserve, we need the determinant of this transition function to be positive. So we need the Jacobian to be positive. In the other notation, if I'm starting at T and I'm going to S, there's our other notation for the Jacobian. We want positive to be orientation preserving, because a positive determinant means that the orientation going from first to second basis element in the domain is the same as going from the first to second image in the range. A negative determinant flips that orientation. A negative Jacobian means it's non-orientable.